So today we're going to discuss on the vector space and subspaces. So let us look at our screen. Um, so here I'll talk about these rules later. So I'll just put this aside, all these rules. Just one second. So in the last sessions we have seen that the column AX is equal to, we are trying to solve AX is equal to B, and we represented that in the form of vectors. So now here we will look into what is a space of the vector uh, without seeing the vector space and especially their subspaces. Um, so let us begin this introduction with introducing this some new things, that is R1. So we denote the vector space by R. This is you can call this as R power 1, R power 2, R power 3, and R power 4, and so on. So what is this R represents? So this R represents that the vector space is of the vector consists of the real components. For example, in the previous tutorial we have previous in the very beginning we have written that linear equation can be written in a form of vector, so that is V, and in terms of columns, for example 1 2. So if we talk about the two equations, so then V is equal to 1 and 2. So 1 and 2 is nothing but it forms a vector, column vector. So now this is nothing but it is a two-dimensional, it is in a two-dimensional space. So then I can write this vector space as R square. So that represents is a two-dimensional. If the vector is a three-dimensional, then it means it has a three linear equations. Then it might be 1 2 then minus 3, something like this, its vector. So then this can be represented in terms of R cube. So generally each space can be represented in terms of R power n. So n represents there are it's a n dimensional space, n-dimensional space which consists of n number of components. So whereas in this case it is three vectors, it has a three components. This vector V has a three components, that is 1 2 and minus 3. It means it's a three-dimensional space. So that can be written as R or 3. So likewise there might be a five-dimensional space and so on. So if you write this definition here, so let me clear this. So then I'll write the definition of the space. The space R power n, so or I don't have, so I'll use this space. So consists of all column vector, all column vectors V with n components. That is what it means. A space R power n consists of all vectors, consists of all column vectors V with n components. So that is the definition of the vector space. So the components of V are real, so that is why we call it as R. So for example, if the components of the vector are complex, for example, if we have a vector component, if we have a vector component, say V is equal to something like this, that is 1 plus I, then 1 minus I. So then these are the vector components. So there are two components in this vector, so this can be represented as C square. So C represents the complex. The components are the complex, so that is why it is represented as C, and it is in a two-dimensional plane, so two-dimensional space, so that is why it is represented as square. Right. So the word space is all those vectors whose means ask us to think of all those vectors, the whole plane. So each vector gives x and y coordinates of point in the plane, so that can be written as, that is, v is equal to x comma y. So now to multiply v by 7, so multiplying every component by 7, it means now the 7 has become the for example, let us take a vector here. Let us take some 5-dimensional vector here. So for example, we'll take v as a column vector which has the 5 components, that is 2, 1, minus 2, 4, 5. It forms 5 dimension. Now if this vector is multiplied by a constant, multiplied um, by say some 7, so 7 is a scalar quantity here. So every component in the vector v is multiplied by this 7. So this is we call it as a scalar operation. To add vectors in R power 5, then add them a component at a time. Means we'll add, for example, we have one more vector, say w, again it is having a 5 components. So if you are adding v plus w, the two vectors, it's added all together at one time. It means we can add any vector in R power n and we can multiply any vector v by any scalar c. So this scalar we can represent normally as c. See, do not get confused with this c with c power 1, 2, 3 or something like that. So this is represents the vector space, the c power 2, because there is a c represents the complex plane, or the components in the vector represents the complex, so it is represented as a c power 2 to represent that it's a complex plane. So whereas this c is a constant, this c which multiplies with the vector is a constant. Uh, for a vector addition and multiplication, it should satisfy certain rules. So that's there are 8 rules that I had written on the right side. So before looking into the rules, so I want you all to see the dimensions and understand the 2-dimension and 3-dimensional space. Oh. Can you see this browser link which I have opened here? Uh, can you tell me, because when I'm switching with these windows, I cannot see these importers. Can you see that web browser content which I have written there? Not sorry, not I have written, which I opened it. Or I have to bring this to a new window. Yeah, I think now you can see this. Here in one of the site we have just visited here. So it defines the introduction to the vectors and its planes and the 3-dimensional space. So basically what you're looking at this diagram is the 2-dimensional space here. It's a 2-dimensional plane which represented by vectors, say a1 and a2. A1 and a2 are the components of the vector here. So it represents the coordinates or the components of vector A. So now, so it defines one particular point. So it has the head and the tail which starts from the uh, is at the initial coordinates. Okay, so uh, we can find the magnitude of this vector A just by applying this Pythagoras theorem. So then you can see this A is equal to root of A square plus B square. So A is 1 point. For example, if we consider this as 1 comma 2, I'll switch back to so let me clear this section here. So for example, if I write this xy plane, it's a two-dimensional plane, and we have, say, vector v is equal to we have 1 3, a column vector. So if we divide this 1 2 3, this is 3 4, and this, if we divide this 1 2 and 3, it means this vector point is here. So it is 1 on x-axis and this is y-axis. So now it is the coordinates, it's starting from 0 0 and goes all the way up to 1 comma 3. So now we can find the magnitude of this vector, that is by applying the Pythagoras theorem, that is just by writing 1 square plus 3 square. So you calculate how much is this, that is 1 plus 9, that is 10. The square root of 10, how much, you see that. So that is the magnitude of this vector. So this is in a two-dimensional plane. The intention of explaining this is to give the idea about the two-dimensional and three-dimensional plane. So like this you can do it. And now if we have two vectors or the 2 points, so how to, for example, here it is given that we have, say, the 2 points, that is at 1 and 2, and one more is at 4 and 6. So how do we calculate the coordinates and the length of the vector? So to find the coordinates and length of the vector, we have to subtract these two vectors. So we'll get one more vector here, so that we can bring it to 0 coordinates, so that it starts from 0 coordinates till such point. So that will give us the magnitude or length of the vector. So this kind of applications examples we have solved in the previous tutorial, where we are discussing initially that the two-dimensional, three-dimensional space. So I just want you to see this. Now the three-dimensional plane looks like this. So I just want to turn this. So the three-dimensional plane it has a 3 components here. If you consider in terms of vector, it means it has a 3 components. So that is A1, A2, A3 in a three-dimensional place and Cartesian coordinates. So we can see this is a right-handed rule, where the middle finger acts as the x-axis, and your thumb acts as y-axis, and the forefinger acts as the z-axis. So then you can see this as the plane, as if you're standing in the corner of a room, then the left side of the wall and the floor can act as the y-axis, and the right wall and the floor joining line acts as x-axis, and the two walls joining it can be acts as the z-axis. So that you can imagine as a three-dimensional space. So even that, with the three-dimensional space, you can find what is the vector. Now for example, this is the vector, the green line which is representing it is a vector. So in this three-dimensional space, we want to find out what is the magnitude or length of this vector. So like this we can do it with the same formula. So now same thing we can see with n dimension. One of the beautiful example of n dimension is, now what is the purpose of studying these vectors beyond these 3 dimensions? Because 3 dimension plane is up to 3 dimensional plane we can write, but beyond the 3 dimensions it is very difficult to imagine. So then the vector it is very easy to represent these in a form of vectors and the coordinates. So now let us see one of the example of this. This is a diagram where you can see it's it is some diagram where we are showing the moment of a body. So here, how many vectors are there? So we are talking about we are talked about the three-dimensional vectors. Now this is an example of how many vectors? Can anybody tell me? So it is on the two-dimensional plane, but here we have nine vectors. So it means we have the nine. If you see this, if I move this moment, that is, this is one of the axis here. So where you can, this is a nine-dimensional plane. It's a nine-dimensional space here, in fact. And this, if you see the moment of this, so this is one of the plane, then this is another plane. So basically for every joint, so there are 1 2 3 4 5 6 7 8 and 9 joints. So there are 9 joints can be defined in a 9-dimensional space. It's very difficult to write in a 9-dimensional space and to explain, but it can be visualized in this way, where we have for example like this. So this is where the vectors plays an important role with multidimensional spaces and its applications. Okay, so now let us switch back to our screen here. So like this, for vectors and its space should satisfy the 8 rules. So I'll just clear this. So we can add any vector in R power and we can multiply any vector v by any scalar c. And when you add any vector in R power n and when you multiply any vector v by any scalar c, then it should be in the same space. It means the resultant should stay in the same space. If it comes in another space, then it means that it is out of the space. Then it violates the 8 rules which the vector has to satisfy. The vector and vector space has to satisfy. So if v is a vector in R power 4 with say for example here we have we have a v is a 4-dimensional uh, plane with 4 components, that is 1 0 1 0 0 1. Then if it is multiplied by a scalar, uh, then that is nothing but it will give us this 2001, sorry, 2002. So I'll get these components in the R space, and this, the new vector should present in the same plane or in the same space. So then it is fine. It means it satisfies all the rules of the vectors. So a whole series of properties that is verified. So first is that it should satisfy the commutative law. It means that V plus W should be equal to W plus V. This is a commutative law. And distributive law is that if you have a constant and if you are adding the two um, vectors here, that is V and W, it should result in C into V plus C into W. If you do this right hand side, it should result in the same thing. So likewise, there is a unique vector 0. For example, if you add 0 plus vector is equal to V. Here 0 vector means that, okay, to make you understand what is a 0 vector, let me go to one of its uh, another term here. Mm, Okay, now we are looking at one more example here from one more website. So this is one plane when we are talking about one plane, and this dot which you represent here, so its components are 0 0 0. It means that the vector components are 0 0. The vector cannot have empty sets or empty components. It has a component, but all the components are 0 0. It means it represents some kind of origin. So that is what this zero vector means. So when you add this zero vector with any of these another vector, then it results in the same vector. Say for example n has some abc. If you add this with a zero vector, so it results in same n itself. So that's what it means. Uh, so now for 0 plus v should result in 0. So likewise there are a couple of rules, 8 rules. So let me bring back these 8 rules now and see these 8 rules. So these are the 8 rules which you are talking about. So uh, these 8 conditions should be satisfied by the vector space. Now for example we have some vector x plus one more vector y. It should result in, the result of this should be same as y plus x. Okay, this is one of the rule. Next, second is y plus x plus z. It means first we add the two vectors y plus z, then we add one more vector x. It should be same as if you add the two vectors x plus y, and then if you add the another vector z. And there is a unique zero vector such that if you add this unique zero vector from x vector, it should result in x itself for all x. And for each x there is a unique vector minus x. It means you have seen this from the 9-dimensional example which I had shown. uh, Let me come back to that and show you this. This. Okay, just observe in this website. So if I take this, you see this eighth vector here, that is 0.49. So in here the 0.49, now it is on the positive axis. Now if I bring back, I can bring back this to say 0. So this is the vector say x in one direction x, and it has the another vector which is a unique in the other direction, that is in terms of minus. So when you add these two, so what do you get? The resultant is 0. So that is what it means here. Yeah. So this we have done, this is done, then this is done. Now 1 times x equals x, and now suppose we have the two scalar constant, that is c1 and c2. If you multiply the two scalar components and then multiply with the vector, it should result in the same thing on the right hand side. That is if we have a constant c2 and first we multiply with the vector and then we multiply c1 to that vector, it should result in the same thing. So this is the another property. So then if we multiply a vector, sorry, here there is a mistake. So this is not x, that is c. C of x plus y means if we have the two vectors x and y and we are adding the two vectors and then multiplying with a constant, it should result in the individual multiplication and then add these two vectors, it should result in the same thing. And then we have the two constants. If we add the two constants and multiply with x, it should result in the sum of these multiplied scalar with these two vectors should result in the same thing. So these 8 rules should be satisfied by this vector space. So if it satisfies, then it means that the all the addition and multiplication, basically on the vectors we are performing two operations, that is addition and multiplication. Then after addition or multiplication, if all these rules are satisfied, whatever the rules that is applicable, then we say that it is in the same vector space. So that's what these 8 conditions are required for every vector space, and there are vectors other than the column vectors and vector space other than r power n, and all vector space has to obey the 8 reasonable rules. A real vector space is a set of vectors together with rules for vector addition and for multiplication by real numbers. So addition and multiplication must produce a vectors that are in the same plane. Means we should not get after addition or multiplication, we should not get any vector which is of other outside the plane. Now let's talk about the 3 vector spaces here. So let me come back and clear this. Uh, the vector spaces other than r power n. So other than r power n, what are the other vector spaces we have? We have a vector space M, we have a vector space F, we have a vector space called Z. So what are these? So M is nothing but it's a 2 cross 2 is matrix. It's a special matrix. The vector space of all real 2 by 2 matrix or matrices. F is a function. Sorry. So the vector space of all real function, all real functions f of x, of all real functions f of x. Now it is a function here, and z is a 0 vector, and the vector space that consists only of a 0 vector. So apart from the vector spaces other than r power n, we have other 3 kinds of vectors. That is M, it means the vector space of all real 2 cross 2 matrix or 2 by 2 matrices. F is a function space, so it is a vector space of all real functions. It means in this vector space we have all real functions, which is represented as f of x. And there is a one more vector space which consists of only 0 vectors. Now if in the M the vectors are really a matrices, and F is a vector or functions, and Z are uh, in Z only addition, say 0 plus 0 will result in 0 itself. So now for M vector space we can add matrix with matrix, and a function we can add in the second function to function we can add, and in 0 vectors we can add 0 vectors, and we can multiply a matrix by 4 or a function by 4 or a 0 vector by 4. That same thing it will result in, it should result in the same kind of vectors. That is, if you multiply 4 with M, it should result in the M itself. M means it should result in matrix itself, 2 cross 2 matrix. Then function should result in function itself, and 0 vector space should result in 0 vector space itself. So the function space F is infinite dimensional. A smaller function space is P is denoted as, a smaller function space is denoted as P or Pn, consisting all polynomials. For example, that is all polynomials are a0 plus a1x plus dash dash plus an x power n of degree n. So this kind of polynomial equations you come across very often. So this is a smaller function space which is represented as P. So we can write this P is equal to a0 plus a1x plus a2 x square plus so on plus a power xn. So here the n represents the degree, and the space Z is a 0 dimensional. It is the smallest possible vector space. So smallest possible vector space means it has r power 0. So which means no components. Not exactly, but it is represented as just 0. So the vector space Z consists exactly one vector, that is 0. No space can do without that 0 vector. It means every vector should start from that 0, so it has to have that 0. So now let us look into the subspaces. So I just let's see this. So now if you see here, you can say this is a it's a 4-dimensional space here. So we have A, B, C, D as represented as a matrix. So we are just talking about here, that is MFZ. The other than the R power n, we have the other vectors as well. So if you can see this, this is a 4-dimensional matrix with M 2 cross 2 matrix. So here the 2 cross 2, that is A, B and C, D. If you define the different values for each of these A, B and C, D, so it represents in a different directions, in a 4 directions. So with A equal to 1 and all other values are 0, so you can see this matrix here which is pointing in the one direction, and then this one more vector here which is pointing in the other direction with B1 and C1 and D1, and for any other values it will point in that respective directions. And the smallest vector which you are talking about, the Z, it is represented by a dot. It means all zeros, so that is this dot. Now let us look into the subspace here. So what is this subspace? So let us read here. After at a different times, we will ask you. So they are the vectors with n components, but may not all of the vector with n components. So what is a subspace? Subspace means they are the vectors with n components, but may not all of the vectors with n components. So all the vectors doesn't have all the n components. It may have less than that. So we will see that in the next coming examples. So what does that subspace means? So there are important vector space inside R power n. So those are subspace of R power n. So here they taken an example of 3-dimensional space of the origin. So then the origin is 0, 0, 0. So that is, it starts from this origin. So that plane is a vector space in its own right. So it's a vector space. So because it has a 3 components, that is 0. If you write in a column vector, this is, see, in this textbook they have given like comma means it goes in the next row. So whenever it is written in a bracket with the comma, it means it's a in a vector you can read this as a 3 rows and 1 column. So that plane is a vector space in its own right. If we add 2 vectors in a plane, their sum is in a plane. If you multiply an in plane vector by 2 or minus 5, still it is in the same plane. So a plane in 3-dimensional space is not R square. So a vector has 3 components and that belongs to R cube. The plane is a vector space inside R power 3. Now let us look into the definition here. What is a subspace? So subspace of the vector space is a set of vectors including zeros that satisfies 2 requirements. If V and W are the vectors in a subspace and C is any scalar, then V plus W is in the subspace and C into V is also in the subspace. So when we add V plus W and multiply the C into D, it is in the same space. So these operations leave us in the subspace. So but when we subtract this V with minus W, what will happen? So we can also subtract because minus W is also a subspace and its sum with V is V minus W. So that depends, again it remains to be in the same subspace. So all linear combination stays in the subspace. Um so every subspace contains a zero vector. So this is one of the fact. This should note it. Every subspace consists the zero vector. The plane r power 3 has to go through 0 0. As I told you, it has to come to its origin. The vector should start from the origin. The vector should start from the origin, that is 0 0. So we mentioned this explicitly for 2m, but it follows directly that rule 2 chose c into v. Now if you multiply c as a constant, so if you multiply with the 0, we are in the same subspace. So planes that don't contain the origin fails those sets. So here one more important point we have to note. So if the planes that doesn't contains the origin that fails origins, then that's those kind of planes will fail to be a test. Now when v is on such a plane that minus v and 0 v are not on the plane, so it misses. So it means it missing the origin. It means it is not in the subspace. So line through the origin are also subspace. So another subspace is all of r power 3. Now the whole space is in subspace. So now if you see here, so any line through 0 0 0 at 0 0 point, or any plane through 0 0, then the whole space or the single vector 0 0 0, that is z. So let us look into an example. If you look into example here, so we'll see here a vector that is x comma y whose components are positive uh, are 0. So the vectors are 2 and 3 is included, but minus 2 and minus 3 is not included. So if we write this here, so let me save this page here. So we are talking about one of the example here, that if v vector is equal to 2 and 3, so if you write this on the two-dimensional plane, so for example let's take the two-dimensional plane with x and y here. So let us split this 1 2 3 and the y-axis 1 2 3. So this is our y and this is x. So in this example it is given, it is 2 3. So now the vector present that this is 2 and this is 3. So it means it starts from the origin, its tail starts at origin and it heads points to 2 comma 3. Now if this vector is multiplied by a constant, that is minus 1, and it says that only this vector space, the positive component, now these vector space consist of only the positive component or 0, but not the negative component. Now if you multiply with this uh, one of the constant, that is minus 2, what do we get here? We will get this as minus 2 and minus 3. Now we have to see that this resultant vector, whether it is in the same plane or it is in a different plane. Now if you look into this, it resulted in minus 2 and minus 3, which is on these minus 2 minus 3 will result in which quadrant? It will result in third quadrant. This is minus 3. If I continue with this, then this is minus 1, minus 2, and this is minus 3. So minus 2 minus 3 will come here. So now the space, it is initially defined that the space whose components are positive. So a vector with a space which consists of only the positives and zeros. It means we have zeros only in this, our vector space is only this one, positive. But the resultant vector after multiplying this, now it has, what happened? The second rule was violated. What was the second rule? The second rule was let's bring back this. What was the second rule? Um Second rule, or uh, if we look at the sixth rule here, it violated. It means C1 into it. Now it's just a one scalar quantity. It's fine. So just we'll consider the C1 into X. It should result in the same C1 into X, or it should result in the same vector space. Since we have not considered this negative vector space, so now the rule has been violated. It is not in the same plane. And to consider this, then we have to consider even this space here. So if we consider even this space, then it means that now the resultant is satisfied. So to satisfy the this second rule, so what we have to do is that we have to even consider this space as well. So if we consider this space, then what happens is that, so now our vectors, the resultant vector is fine. It is, we can consider that it falls in the same space. So now we have the two quarter planes. We can multiply by C, but rule 1 fails. Now let us continue with the same example here and see. Now if we have the same vector, that is 2 and 3, and we have one more vector here, W is equal to -3 and -2. Let's see whether it will fall. What is the resultant? Whether it will fall in the same these two quadrants, that is first quadrant and second quadrant. If it falls in these two quadrants, it means it is in the same vector space. Otherwise, it violates the rule. So let us add this V plus W, which is equal to, our V is 2 and 3, and our W is -3 and -2. So what do we get here? The resultant vector. The resultant vector, we will get this as -1, and we'll get this as 1. Now if you see, now it doesn't fall in the same planes. Now we have the two planes, one plane in the first quadrant and second plane in the third quadrant. But this resultant is again failed. It failed to satisfy the first condition. So that is W plus V. So now it doesn't fall in the same vector space or the quarter plane. So now to make this rule satisfy, what I need to do, I have to include one more vector space here. So this -1 and 1 means this is -1 and 1. So it means it will fall in this second quadrant. It means I have to consider even this quadrant as well to make this vector space to fall or to satisfy. So this is what just a simple example to make you understand. So when we perform certain addition or multiplication, whether the resultant falls in the same uh, plane or it falls in the different plane. Basically it's supposed to fall in the same plane because we have considered whatever the plane we have considered or the space we have considered. If it falls outside, then it means it violates the rule. So a subspace containing V and W must contain all linear combinations, that is C into V plus D into W. Okay. So there are a couple of examples with respect to vector matrix. We will see this in the next coming classes. Thank you.